normalized in a suitable way. For each natural k, we take the cosine function, also suitably normalized. Ek of t is given by the following formula. And fk of t will be the respective sine function, also normalized. Here k is a natural number. Then an explicit computation shows that E0, Ek, and Fk, where k runs over natural numbers, is an orthonormal family. So this is a so-called trigonometric system. It is absolutely classical, and you probably know about the system from your calculus course. It appears in many applications and many problems related to mathematical physics. And in fact, long ago, it is exactly this system which gave birth to the abstract notion of a Hilbert space. Example 4. Again, the trigonometric system, but now in a slightly different form. So again, H is the big L2 space on the same interval from minus pi to pi. And we denote by En of t the following exponent. Here, n can be any integer. Again, it's very easy to calculate that the resulting family is orthonormal. En is an orthonormal family. This family is also called the trigonometric system. Of course, it is formally different from the system in example 3. But these systems, this one and this one, are related to each other by a very simple unitary transformation. So each of them is usually called the trigonometric system. And perhaps the most elegant way to write the trigonometric system is to move from the interval to the circle. And this is our example 5. Example 5, again, the trigonometric system, but this time on the circle. So as usual, we denote by bold T the unit circle on the complex plane. And as usual, we equip with the normalized length measure. So the length of the whole circle will be equal to 1. And our space H will be L2 on the circle. And for each integer n, we define function En by the following simple formula: z to the power n. Again, it's very easy to show that the resulting countable family is orthonormal. If we identify L2 on the circle with L2 on the interval, so we fix the standard unitary isomorphism between them, which was briefly discussed at the previous lecture, then the functions En from example 4 will correspond precisely to the function En from example 5. And this is the reason why this family is also called the trigonometric system. The advantage of this form of the trigonometric system is that it consists precisely of unitary characters of the circle. So in general, a unitary character of a group is a group homomorphism from this group to the circle. But circle is itself a group, and these functions are precisely the continuous homomorphisms from the circle to itself. And in fact, this example can be generalized to more general situations, for example, to any compact abelian topological group. Okay, example 6. This is now something different. This is the Rademacher system. Now the Hilbert space H is L2 on the interval 0, 1. And our functions Rn are given by the following explicit formula. This is the sign of the following function. So this is the formula, and explicitly to understand what these functions look like, how they look like, just let's draw a picture. So to draw R1, we divide the interval from 0 to 1 into 2 pieces, and we draw the following picture. So this is 1, and this is minus 1. So this is the graph of the function R1. To get R2, we divide the interval from 0 to 1 into 4 equal pieces. And we draw a similar picture. We have 1 here, minus 1 here, gain 1 on this subinterval, and minus 1 here. And this is R2. And so on. So to get R3, we divide the interval into 8 pieces and do a similar construction. So again, it's very easy to see that the resulting family Rn, where n runs over natural numbers, is orthonormal. So this is the so-called Rademacher system. It also has many useful applications, both in analysis and also in some applied fields of science. And also it is related to probability, because actually these functions can be interpreted as independent random variables taking values +1 and -1 with probabilities 1/2. Okay, so since we are most interested in separable Hilbert spaces, let's start by proving the following simple proposition. Proposition 1. If H is a separable inner product space, and if EI is an orthonormal family in H, then it is at most countable. But the index set I is at most countable. Well, the proof is basically an argument of kind of something similar to the Dirichlet principle. So if you have uncountably many boxes and countably many rabbits sitting in them, then there are boxes with no rabbits inside.
Excuse me, why we can just say that they all are linear independent?
Well, they will be automatically linearly independent because of the orthogonality.
Okay.
This is, well, I forgot to, maybe I should have said that, but this is a simple exercise. So a family of non-zero orthogonal vectors is automatically linearly independent. Okay, so why is it most countable? First of all, we observe that the distance between EI and EJ by the Pythagorean theorem is the square root of 2 whenever I and j are different. So if we take sufficiently small open balls of radius, so this implies that for each r less than or equal to square root of 2 divided by 2, the respective open balls centered at EI and EJ don't intersect. The intersection is empty. Okay, let's now take, we assume that H is separable, so let's take a countable dense subset, say Xn. Dense subset of H. Well, since it is dense, it intersects each non-empty open set. In particular, it intersects each such ball. So for each I in I, there exists a natural number n of I such that xn of I sits in the respective ball. So we get a map, the map from I to the natural numbers, which takes I to n of I. So what can we say about this map? Since our balls are disjoint, we see that this map is injective. This map is injective. But this obviously implies that I is at most countable. And this completes the proof. Okay, let's now introduce Fourier coefficients of a vector with respect to an orthonormal family. So as before, we suppose that H is an inner product space. H is an inner product space. Suppose that EI is an orthonormal family in H, and X, let X be a vector in H. Then the inner product of X and EI, this is a complex number, and this number is called the ith Fourier coefficient. Fourier coefficient of X with respect to the family EI. Our next result gives probably the most important geometric property of Fourier coefficients. This is our proposition 2. Suppose that we have a finite orthonormal family E1 to En. This is an orthonormal family in H. Let H0 denote the finite dimensional space spanned by E1 to En. Let X be a vector in H. And let's see I denote the ith Fourier coefficient of x with respect to this family. Then, first of all, I claim that the following vector y, given by the following formula, this is finite sum from 1 to n, this vector is the orthogonal projection of x onto H0. The orthogonal projection of x onto H0. And part 2, we have the following explicit formula for the distance between x and H0. So this distance, the square of this distance, equals the following expression. Okay. To prove part 1, so what we want to do, let's recall it that the orthogonal projection is an element y such that x minus y is orthogonal to H0. So we want to show that x minus y is orthogonal to H0. But since you want to n form an algebraic basis of H0, it suffices to show that x minus y is orthogonal to each of them. X minus y is orthogonal to ej for each j. And this is an explicit computation, so we calculate the inner product. And this is x ej minus, so we substitute this vector y here and use the linearity of the inner product in the first variable. And now, since our family is orthonormal, only one summand survives here, namely only Cj survives. And this is 0. Okay, so this shows that y is indeed the orthogonal projection. And the second part is a simple application of the Pythagorean theorem. So if we calculate the length of x squared, then the Pythagorean theorem implies that this is the norm of x minus y squared plus y squared, because these two vectors are orthogonal to each other. Now let's recall that the orthogonal projection is the nearest point to x in H0. So this distance is precisely the distance between x and H0 squared. And the norm of y is also calculated by the Pythagorean theorem. So this formula, together with the Pythagorean theorem, implies that the norm of y squared is the following sum. So this is equivalent to the second part of our proposition. Okay. So in this proposition, we considered a finite orthonormal family. So from now on, we fix an at most countable orthonormal family. So from now on, we assume that, as before, that H is an inner product space. And we fix an at most countable orthonormal family EI. At most countable orthonormal family. By the way, let's introduce an abbreviation. So AMC will mean at most countable. At most countable orthonormal family in H. So it is at most countable, so we may assume that I is either the natural numbers or the finite set of natural numbers from 1 to n. We now have the following simple corollary, simple but useful corollary of the previous proposition. If X is an element in H, and if Ci is the ith Fourier coefficient of X with respect to this family, then the following inequality holds. And this is the so-called Bessel's inequality. So in particular, we see that if our family is countable, strictly countable, then the respective series converges. In particular, if I is the set of natural numbers, then the respective series converges. Well, this is immediate from the second part of our proposition, because the left-hand side of this equality is always non-negative. And so the right-hand side is also non-negative. So this gives us the proof in the case where I is finite. And if I is countable, we simply pass to the limit as n goes to infinity, and we get both the convergence of the series and this inequality. So this follows from part 2 of the previous proposition, proposition 1. Okay, we now give the following definition. The Fourier series of an element X in H with respect to our family, to our orthonormal family, which is, as before, assumed to be at most countable, is the following formal expression. Here, Ci denotes the ith Fourier coefficient of X with respect to our family. So at this point, the Fourier series is only a formal expression. So I don't claim that it converges. I don't claim that it converges to X, and in general, I don't claim that it converges in H. We will see soon, however, that if H is complete, then this series always converges. Not necessarily to X, but always converges. But at this point, this is a formal expression. Proposition 3 describes some simple elementary properties of Fourier series. So part 1. Let X be an element in H, and suppose suppose that x can be written in the following form. I claim that in this case, AI is each coefficient, AI is precisely the Fourier coefficient of x for each I. So this statement is the so-called uniqueness of the Fourier series. And part 2, so suppose we have now two vectors in H, and suppose that each of them can be decomposed in the following way. In this case, we have the following explicit formula for their inner product. The inner product of x and y equals the following sum, Ci di complex conjugate. And in particular, we have the following so-called Parseval's identity. So this is the special case of the previous formula in the case where y equals x. And this is the so-called Parseval's identity. The proof is more or less straightforward. To get part 1, we simply calculate the Fourier coefficients of x explicitly. So the inner product of x in EJ. So we substitute this expression here. Here we use the fact that the inner product is continuous. So if I is countable, then we can use the continuity of the inner product and write this formula. And this is nothing but AJ. So only one summand survives here. And this proves part 1. And to prove part 2, we also explicitly substitute x and y as infinite sums in the inner product. Again, using the continuity of the inner product, we can write the following expression. But again, since our family is orthonormal, only those summands survive where I equals j. And so we get the following sum. Okay. Let's now discuss the existence of orthonormal families. It would be great to construct a sufficiently large orthonormal family, at least by analogy with the finite dimensional case. So in the finite dimensional case, well, at least over the real numbers, you probably know from your course of geometry that in each Euclidean finite dimension Euclidean space, there exists an orthonormal basis. It turns out that in the infinite dimension situation, we have at least 3 ways to define sufficiently large orthonormal families. So we give the following 3 definitions. We say that our family, EI, is, first definition 1, we say that it is an orthonormal basis. An orthonormal basis if each element x in H has the following form. Where Ci are complex numbers. But in fact, we already know that if such formula holds, then Ci are nothing but the Fourier coefficients.
Well, it can be not the basis.
Yes, this is important. So an orthonormal basis in an inner product space is not necessarily a basis in the algebraic sense. And we will see soon that if H is a Hilbert space, an infinite dimensional Hilbert space, then an orthonormal basis is never an algebraic basis. Definition two, we say that our family EI is total if the nearest span of this family is dense in H. And definition 3, we say that EI is maximal if it is not properly contained in any strictly bigger orthonormal family. It is not properly contained in a larger orthonormal family. So it is maximal with respect to the usual, to the natural order on the set of all orthonormal families. More explicitly, this means that this is equivalent to say that the orthogonal complement of our family is trivial. So there is no vector which is orthogonal to, there is no non-zero vector which is orthogonal to all of them. Okay, so in some sense, each of these properties means that our system, our family is big. Let's now look at relations between these properties. So we have the following theorem. I claim that in the general case, conditions 1 and 2 are equivalent, and they imply condition 3. And if we assume that H is a Hilbert space, if H is a Hilbert space, then all the conditions are equivalent. All of them are equivalent. Okay, let's now prove this. First of all, it's clear that 1 implies 2. This is clear because if we know that each element x has its foreign, so if I is finite, then there is nothing to prove. It's finite linear combination. And if I is the set of natural numbers, so if we have, if this is an infinite series, then x is approximated by finite sums, and so it lies in the closure of this linear span. So the linear span is dense. So 1 implies 2. Let's now show that 2 implies 1. So this is not so obvious, and this will use the fact that we work in the inner product space. So for each k in I, let hk denote the linear span of E1 to ek. By assumption, for each x in H, so each element in H can be approximated by finite linear combinations of our elements of our orthonormal family. So for each positive epsilon, we can find an element k0 in I such that the distance between x and hk0 is smaller than epsilon. This follows from condition 2. Okay, so since this holds for some k0, the same inequality obviously holds if we take k bigger than k0. So our subspaces form an ascending chain, and this implies that for each k greater than or equal to k0, we have the same formula. The distance between x and hk is less than epsilon. But we already have an explicit formula for this distance. By proposition 1, this is the distance between x and the orthogonal projection onto hk. And the orthogonal projection is given by the following formula. This is the sum from 1 to k of ci ei, where ci is the Fourier coefficient. Okay, so we have proved that for each positive epsilon, there is a number k0 such that whenever k is greater than or equal to k0, we have this inequality. This is precisely the definition of a convergent series. So this implies that x is the sum ci ei. Of course, in the case where I is finite, this is more or less trivial because this will be 0 if k is big enough. But if I is countable, then we have the convergence of the series to x. Okay, so we now see that 1 and 2 are equivalent. Let's now show that 2 implies 3. 2 implies 3. Well, this is very easy. If we know that our family is total, and we want to show that it is maximal, so we want to show that the orthogonal complement to this family is trivial. Well, we know that the orthogonal complement equals the orthogonal complement to the closure of the linear span of this set. But since our family is total, the closure of this linear span is the whole of H. And of course, the orthogonal complement of H is 0. And so this implies that our family is maximal. Okay, and finally, let's assume now that H is a Hilbert space. And let's show that 3 implies 2. So we assume that our family is maximal, and we want to show that it is total. Okay, let H0 denote the closure of the linear span of our family EI. Since H is a Hilbert space, we can apply the orthogonal complement theorem. So the orthogonal complement theorem implies that H is the direct sum of H0 and H0 orthogonal. Okay, but by assumption our family is maximal, so the orthogonal complement of H0 is trivial. So this is 0 by assumption. And we see that H equals H0. But this means precisely that the linear span is dense in H. So this completes the proof. In general, if we don't assume completeness, then 2 and 3 are not equivalent. And there is a respective exercise in our next exercise sheet. Okay. Now our goal will be to show that each separable inner product space has an orthogonal basis. And here's a key lemma. A key lemma. Suppose that H is an inner product space. And suppose that Xi is an most countable, linearly independent family of elements in H. So it is most countable. So we may assume that I is either the set of natural numbers or set of integers from 1 to n. For each k in I, let hk denote the linear span of x1 to xk. So this is a finite dimensional subspace in H. I claim that there exists an orthonormal family in H, a family EI of the same cardinality as Xi, so it is indexed by the same index set, such that for each k in I, the linear span of E1 to Ek equals Hk. In other words, we can replace our linear independent family by an orthogonal family, orthonormal family, in such a way that these linear spans remain the same. The proof is absolutely classical. This is the so-called Gram-Schmidt orthogonalization process. So we use induction on K. First of all, we define E1 as follows. This is just x1 normalized. And we assume that the elements E1 to Ek are already constructed. Or better, Ek minus 1. Now let's construct Ek. First of all, we introduce an auxiliary vector Ek prime. This will be xk minus the orthogonal projection of xk onto hk minus 1. So explicitly we know the explicit formula. This is the sum from 1 to k minus 1. Here we have the Fourier coefficient EI. So by the definition of the orthogonal projection, we see that this element ek prime is orthogonal to hk minus 1, and it is not zero. It is not zero because our family is linearly independent. So xk is not in hk minus 1. And so this element is not zero. So now we normalize it. We let ek be ek prime normalized. And this implies that E1 to k is an orthonormal family, and the linear span of this family equals hk. So now the induction argument shows that the required family is constructed. We now have the following theorem. Each separable inner product space has an at most countable orthonormal basis. To prove this result, we first use the assumption that our space is separable, and we choose an at most countable total linearly independent family in H. So we choose an at most countable linear independent family xi in H such that the linear span is dense. This is always possible. In fact, this is a part of an exercise from sheet 1. So first of all, we choose a dense countable subset, and then we somehow throw away some elements of the set to get a linearly independent set with a dense linear span. And then we apply the orthogonalization process. We apply the orthogonalization process to this family, and we get an orthonormal family in H with the same linear span. So linear span of EI is dense in H. And by our previous theorem, this means precisely that EI is an orthonormal basis. So this completes the proof. Okay, let's now look at some concrete examples of orthonormal basis in Hilbert spaces. Example 1, if H is Cn, and if EI, as before, is the following vector in H, then it's clear that E1 to En is an orthonormal basis. An orthonormal basis in H. In this case, it is also an algebraic basis. That is clear. Example 2. Example 2. Now H is little L2, the space of square summable sequences, and we define EI by a similar formula. But now our sequence is infinite to the right. Well, it's more or less immediate that EI is an orthonormal basis in H. Well, simply because if we take the linear span of all these vectors, we get the space of finite sequences, the sequences which are eventually zero. And a simple argument shows that this space is dense in L2. So it is an orthonormal basis. But it is essential that this is not an algebraic basis. It is not an algebraic basis. The linear span of this sequence is strictly smaller than L2. Example 3. It's a standard fact. I wouldn't say that it is trivial, but it is classical. And I hope you know this fact from your calculus course. The trigonometric system is an orthonormal basis in L2 or on the interval, or if you like, in L2 on the circle. This is a classical fact. There are several proofs. Maybe the shortest one is based on the Stone-Weierstrass theorem, but of course there are more straightforward and classical proofs. Example 4. Oh, by the way, a non-example. A non-example, the Eurodomar System. And by the way, this is a simple but useful exercise. The Eurodomar System is not an orthonormal basis in L2 of 0, 1. So its linear span is not dense, and the orthogonal complement is non-trivial. But on the other hand, if we somehow enlarge the Eurodomar system, if we add, more explicitly, if we add all finite products of Rademacher functions, then we get a so-called Walsh system, and it is known that this system is an orthonormal basis of the big L2 space. Example 4. Example 4. Now let H be the big L2 space on the real line. Of course, the real line is equipped with the Lebesgue measure. And we introduce the following family of functions, we denote by xn of t. The following function. So it's easy to see that this function indeed sits in the big L2 space. Here n runs over all non-negative integers. This family is not orthonormal, but it is linearly independent. So we can apply the orthogonalization process. And by applying this process, we get an orthonormal family, Hn. The functions Hn are called Hermite functions. So it's an orthonormal family in the big L2 space. And a useful exercise, which is not very easy, but more or less classical, is to show that the family of Hermite functions is an orthonormal basis. Hn is an orthonormal basis in the big L2 space on the line. The proof uses properties of the Fourier transform on the real line.
So what is the range of n here? Is it
Oh, of course, thank you. The same set of non-negative integers. Thank you. Okay, now we are able to prove the classification theorem for separable Hilbert spaces. Part 1. Suppose that H is a separable, infinite dimensional Hilbert space. So we choose a countable orthonormal basis. Let EI be an orthonormal basis. We know that it exists, and of course it is infinite because the space is assumed to be infinite dimensional. An orthonormal basis of H. I claim that the map, which will be denoted by U, the map U from H to the literal L2 space, which takes each vector x to the sequence of its Fourier coefficients, is a unitary isomorphism. Is a unitary isomorphism between H and literal L2. So in particular, we see that each separable infinite dimensional Hilbert space is unitarily isomorphic to literal L2. And part 2 is much easier. This is a similar result about finite dimensional Hilbert space. So if H is a finite dimensional Hilbert space, then we may choose a finite orthonormal basis of H. And I claim that the map U, which now acts from H to Cn, and is given by the same formula. It takes x to the sequence of its Fourier coefficients, is a unitary isomorphism. Is a unitary isomorphism. So this result gives us a complete classification of separable Hilbert spaces up to a unitary isomorphism. Okay, let's prove part 1. First of all, we already know we have Bessel's inequality, which means that this sequence is indeed an element of literal L2. So this sequence is square summable. Bessel's inequality implies that U indeed takes H to L2. Well, obviously it is linear. U is linear. This is clear. And it was proposition 2, so elementary properties of Fourier series. So proposition 2 implies that U preserves the inner product. The inner product of Ux and Uy taken in L2 equals the inner product of X and Y in H. For each X and Y in H. So to complete the proof, we must show that U is surjective. It preserves the inner product, so it is isometric. As a corollary, it is injective. And now we have to prove that it is surjective. Okay, to prove that U is surjective, let's introduce the space of finite sequences. So let's C00 denote the space of finite sequences. That is the space of sequences which are eventually zero. There is n such that xi vanishes if I is bigger than n. So this is a vector subspace in L2, and we have the following 3 simple facts about this subspace. Fact A, C00, the space of finite sequences, is dense in L2. Well, if we take an arbitrary vector x in L2 and truncate it, so write zeros at the positions bigger than n, then the truncated vectors will converge to x. So this space of finite sequences is dense in L2. The second fact, which is also clear from the construction, is that C00 is contained in the image of U. C00 is contained in the image of U. This is also clear because U clearly takes the linear span of our orthonormal basis precisely onto C00. So this implies that the image of U contains C00. And finally, fact C, the image of U is closed in L2. Well, why is it closed? It is closed because H is complete. H is a Hilbert space, so it is complete. And the image of U is isometrically isomorphic to H. So it is also complete. The image of U is complete, but a complete subset of a metric space is necessarily closed. So if we combine these facts, we conclude that U is surjective. So the image of U is closed, but it contains a dense subspace, so it is itself dense. Well, it is dense and closed simultaneously. This means that it is the whole of L2.
Why image of U is closed?
Well, we assume
It's complete itself? Okay.
Well, H is complete by assumption. The image of U, well, U is, we know that U is, U preserves the inner product. Since it preserves the inner product, it is an isometry. So it is an isometric isomorphism of H onto its image. U is an isometric isomorphism of H onto its image. So the image of U is also complete. H is complete, and so the image of U is complete. But a complete subset of a metric space is closed, always. So this implies that the image of U is closed. Okay, so this completes the proof in part in the infinite dimensional case. The proof of part 2 is similar, and in fact it is much easier than the proof of part 1. So we begin in the same way. We take and we observe that this map U preserves the inner product, so it is injective, but the dimensions are the same, and so it is an isomorphism. So this completes the proof of the classification theorem. As a corollary, we see that there exists an isometric, a unitary isomorphism. There exists a unitary isomorphism between the big L2 space on the real line and the little L2 space on the set of all non-negative integers, which takes the Hermite functions Hn, to the standard orthonormal basis of the little L2 space. So here Hn are Hermite functions, and En is the same En as before. This isomorphism has a deep physical meaning. In fact, this isomorphism establishes an equivalence between two mathematical pictures of quantum mechanics, namely the matrix quantum mechanics of Heisenberg and the wave mechanics of Schrödinger.
Can I have a question about measure spaces? We can have L2 or any measure space.
Yeah.
Can we have some good criteria for this L2 to be separable?
We have some, well, there are some sufficient conditions, but I'm not sure about the criterion.
What's sufficient condition? Is it sufficient that the measure space is sigma finite?
No. Well, in fact, this, maybe I'm not entirely right, because of this, of course, this condition can be formulated in terms of measure space, but it is not equivalent to sigma finiteness. In fact, it's rather easy to construct a finite measure space for which the respective L2 space is not separable. So this is not related to the property of being sigma finite. This is called property of having a finite of countable basis of a measure. But this is some technical property of a measure. So anyway, this is not related to the property of being sigma finite. Well, if you don't mind, in conclusion, I'd like to formulate one simple but important corollary of our classification theorem. It's the so-called Fischer theorem. Fischer theorem. This theorem states the following. Suppose that H is a Hilbert space, and suppose we have a countable orthonormal family, Fn, a countable orthonormal family in H. Then for each square summable sequence Cn, that is for each element Cn in L2, the following series Cnfn converges in H. This theorem can be proved in a rather straightforward way, but from our point of view, it will be much more convenient to prove it by using the classification theorem. Indeed, let's take the closure of the linear span of this family, and let's denote it by H0. So H0 is a separable Hilbert space, and Fn is an orthonormal basis of H0. So our theorem implies that there exists a unitary isomorphism. A unitary isomorphism U from H0 to little l2, which takes each Fn to the nth factor of the standard orthonormal basis of L2. Okay, but if we replace here Fn by En, and if we look at the respective series in the little L2 space, then it is absolutely obvious that it converges. Namely, it converges to C. And now to complete the proof, it remains to apply the inverse map, U inverse. And we conclude that U inverse of C is the sum Cn Fn. And so this series converges. And this completes the proof. So there is a traditional approach to this theory. So in the traditional approach, one first proves explicitly there is Fischer theorem, and then deduces from it the classification theorem. But in my view, the opposite order is more natural. So first we prove the classification theorem, and then the Fischer theorem becomes a simple corollary. Okay, so that's all for today. And at the next lecture, we begin to discuss linear functionals on norm spaces, and we prove one of the fundamental principles of functional analysis, namely the Hahn-Banach theorem.